Okay. Whoa. Good morning, everybody. Thank you for coming. This morning, I'd like to say a few words about challenges in microwave filter design, and we'll hit a few key things in a short time, and the organizers also asked me to say a few things about 5G, because of course, everybody wants to hear about 5G, so we'll do a little of that too. So we can talk about maybe two or three broad categories here. The first is design. We need to be efficient and we need to be accurate. And accurate translates into EM simulation these days. There's a very tight marriage between filter design and EM simulation. And the nice thing about filters is there's an exact answer. And if you're not getting that exact answer, there's got to be a reason. So it's a good test bed for your EM simulation. And then, of course, in manufacturing, cost is a key issue. And in commercial products like cell phones or the cell phone network, high volume is, of course, an issue. And if we probably should have put cost up in the design category as well, because if you're not designing for cost, you're never going to get there if you just throw it over the wall into manufacturing. And then in the 5G world, we'll say a few words about the millimeter wave backhaul. And of course, everything above applies to that problem, but now we're doing it at millimeter wave frequencies instead of lower frequencies. So let's talk a little bit about design strategies. There's at least three options we could think about here. The first is classic ladder synthesis, which has been around for a while. A little bit newer approach is the coupling matrix synthesis. And then I'm going to say a few words about basically designing by optimization and using very little synthesis actually, and doing a lot of work just with optimization. When the circuit simulators first became popular in our business, this was kind of heresy in the filter community. If you mentioned optimization, and a few people would make their blood pressure go up. But of course today, we're much more comfortable with it. So let's talk about design by synthesis. The classic ladder synthesis is still limited to commensurate distributed networks or lumped networks, but after all these years, we still don't know how to mix the two. It's got to be one or the other. And we can get a good basic circuit, but there's a lot of details that we can't synthesize directly. Like if you're doing a Combline or an interdigital filter and you want tapped resonators at the input and the output, you have to add those later, usually by optimization, because they can't be directly synthesized. It's not commensurate with the rest of the network. Other details like the tuning screws also have to be inserted, usually by optimization. So there's some complex programming required. Numerical precision becomes an issue with synthesis. And the complexity of the whole process can sometimes get in the way of intuition. You go through your synthesis and you've got impedance levels or something that's not coming out quite right. So you have to go back to the beginning, but you're not quite sure what to do different at that point in order to get to a better solution. Then coupling matrix synthesis is also very popular, but the coupling matrix is really an idealized lumped element network when you translate it into the bandpass domain. It's a narrow band approximation. Again, details like tapped resonator are not there. You're going to have to put those in later. Again, some programming is required, and there's some trial and error involved too, particularly if you're going after a new topology that hasn't been done before. And I'm going to show you that at times it can give you some misleading results that you need to be aware of. Well, what about design by optimization? Well, most general purpose optimizers aren't very efficient if you're trying to do a filter. You might get a good result, you might not. Many times one resonator you may lose control of one resonator and it goes out of the passband. You may end up with a certain bandwidth and the optimizer doesn't know how to bring the bandwidth back in to where you want it, because in fact you're meeting the spec. If the bandwidth is too wide and you've got a return loss spec, you're meeting the spec. So it doesn't know what to do with that. But a filter has a very well-defined response. There's a mathematical foundation there that if we think about it and if we're willing to write a custom optimization routine, there's a lot of leverage there. And of course, for a lossless Chebyshev filter, we know what that response looks like. It's an equal ripple insertion loss and return loss in the passband. And if we add cross couplings to our network, that goal is still the same. We're still looking for an equal ripple passband. So nothing has changed as far as the optimization goals. So if we can consistently find this equal ripple passband, we can design a filter or tune a filter using optimization. And we can either work on an accurate network theory model, or we may be working on an EM-based model. We might be port tuning an EM-based model. So here's a Chebyshev Combline filter, and we've got the equivalent circuit here. And this equivalent circuit is actually quite accurate. We're including frequency-dependent couplings between the resonators. This is a series shorted transmission line, so its coupling is frequency-dependent. This tapping circuit here is due to Bud Crystal, who worked this out. And the resonator is actually here. This is a correction factor for the tap added by Crystal. And if you could see it, it's fairly high impedance, and it's actually a negative impedance. And our tap line is out here with a known impedance and a known length. So this is as close as we can get, basically, to reality. And so starting from this starting point, we can then add cross couplings to this circuit simply by putting an element in place and adjusting the value of the element so the coupling is very weak, and then we gradually increase the strength of that coupling and optimize along the way as we're going. And your desired transmission zero will appear at some point, and then you can control its position. So we can design any number of filters either using this folded form or the cascade triples and quads approach, and do it all without actually ever doing any synthesis. So some of the coupling matrix programs, you put in a requirement, and at the end it may spit out a long laundry list of possible topologies. But in reality, the size and the position of our resonators are typically pretty restricted by the specification that we're given. So there's really only a few topologies that we can really make work for any given design challenge. The basic rules for adding those cross couplings are very simple. We know how to place zeros above and below the passband. And again, starting from the Chebyshev prototype, we can grow that cross coupling in by optimization. And we don't, for the simpler cross coupled filters, we really don't have to do any synthesis. And if our optimization routine is fast and it returns us to an exact equal ripple response every time, then this method is actually quite intuitive and quite fast. And I'll show you what that looks like in just a few minutes here. And we're generally working on a circuit model or an EM model that is often more reliable than the coupling matrix. So here's let's look at an n equals 6 filter. This happens to be for the Wimax band, and we're going to use the folded form here, and we're going to add a cross coupling between these two resonators and another cross coupling between these two. This is an 8, but we're going to design a 6. So in the coupling matrix software, it says, great, yes, you can do this, no problem. And it's a very symmetrical response. And as we change the reject level, that symmetry is maintained. So as the reject level moves up and down, it always stays perfectly symmetrical. So if we want an equivalent circuit of that, in the literature, when people talk about coupling matrix, you often see these loop circuits. But in a schematic capture environment like this, that's very difficult to work with. And in Bianchi and Sorrentino's book, they show this form, which is more of a nodal form, but it's still a coupling matrix equivalent circuit, and it's much easier to work with in a schematic capture environment. And in Microwave Office, they have this really neat coupled inductor model, so that the self-inductance, of course, is our resonator, but then every possible non-adjacent and adjacent coupling is available in this model. So it's very convenient for experimenting with various coupling matrices. And in fact, you can basically synthesize a coupling matrix using a circuit like this by optimization. So I'm not showing all the possible couplings here, but I've got the mainline couplings, and then I've got the two cross couplings are in play here in this circuit. And if we look at the frequency response, it indeed looks very much like what we saw in the coupling matrix software. In fact, the software is either deriving what it showed us from the matrix itself. So, and again, it's very symmetrical, just like we saw in the software. But we can, sorry. So we can tune on this circuit. I've got my two cross couplings up here, and I'm gonna start a little animation here. And first we'll tune on the negative cross coupling, which is the capacitor, and then we'll tune on the positive cross coupling, and let's just see what happens. Here we go. Okay. So tuning on the capacitor there, and notice as I tune, everything stays symmetrical. So I'm going to bring the reject level up about 5 dB higher than it was when we started. And of course, as we tune those cross couplings, we're detuning our passband. We'll fix that with the optimizer. Here's our equal ripple optimizer. We just fixed our passband, and now we need to go back and touch it up again, the cross coupling. And if we optimize it one more time, in about 7 or 8 iterations of the optimizer, it brings us back to a perfectly equal ripple response. And what this is what I'm doing here is I'm taking advantage of the scripting and the COM interface in Microwave Office to write my own optimization software, and then I use the models and the analysis engine in Microwave Office, because it would be impossible to recreate all the work they've done on the models and everything. But I have an opportunity here to apply my IP, my knowledge of how I want to do the optimization without having to reinvent the rest of the simulator. So this is a compiled executable program that runs in conjunction with Microwave Office. So we've seen how the zeros move and the lobe levels move on the coupling matrix model. Let's look at the circuit theory model now and see what that does. So here's our basic Combline equivalent circuit, and literally we just add in a lumped capacitor here, and we add in a series shorted line here for the positive cross-coupling. So this is going to be an iris from resonators 1 to 6, and this is a capacitor from resonator 2 to 5. And again, we start with a very small capacitor and a very large impedance inductor, and we gradually modify those elements and re-optimize as we go, and end up with a cross-coupled filter. So here's the result of that. And you notice that we're meeting our specification here on the high side, but something has gone wrong here on the low side. The zeros aren't distinct like they were in the prototype. And we can retune the circuit so that we're actually meeting the spec on the low side, but then the high side goes out. And in fact, there is no solution in the circuit theory model that's perfectly symmetrical like the coupling matrix was. So we can tune on that a little bit and verify that that's indeed the case. So again, we'll modify the couplings here, and we'll use our optimizer again to bring it back to equal ripple every now and then. We're not going very far with the tunings here, so now I'm varying the inductor first, and you can see the low side is maybe getting better, but we're starting to lose the high side. And I'll go back the other way a little ways. And now I'll put the inductor back where it started, and I'll modify the capacitor. And that's going the wrong way. But now I've got the low side very close, and notice the high side is pretty far out. And we need to re-optimize the passband. And we can fine-tune that low side a little bit more, but again, it'll never become perfectly symmetrical like the coupling matrix predicts. So which one is right? Which one's right? How do we know? Well, let's build a 3D FEM model of our filter, and we'll use that as our benchmark. So here's our filter model in HFSS. We could also do it in Analyst or CST. We've got our input and output here. Here's our capacitive probe that's connecting 2 to 5. And here's our iris that's providing a coupling from 1 to 6. And these little blue rectangles are extra ports that I've added into the model so that I can port tune this model. So instead of analyzing a 2-port here, we're actually analyzing an 8-port circuit. And when we bring it into the circuit simulator, we can use very fast circuit theory simulation to modify our project. And what I've done in this case is I actually ran the simulation several times, and I fine-tuned the length of the probe, and I fine-tuned the width of this iris so that I'm meeting the high side goal exactly in the HFSS simulation, just so we can do an easier comparison. So here's our port tune circuit, again in Microwave Office. What I tend to do these days is this symbol, this rectangle is my S parameter data. I tend to draw a custom symbol that kind of fits my geometry, which just helps my thinking and helps the communication with other people. And that's actually very easy to do, so it's something that you maybe want to look at. So these capacitors are going to tune the frequencies of our resonators, and I've put another inductor here in parallel with the existing couplings in order to fine-tune the couplings in our EM model. And again, the equal ripple optimization is a key element in this port tuning process, because if we don't come back to the same known solution every time, then all we've done is introduce noise into the process. And you can literally drive the tunings if you want to. You can keep modifying the geometry so that the tunings that we apply here become very, very small. And at some point, they literally get down into the noise. So here's the result. Here's our HFSS model is the black line for the transmission, and the red line is the equivalent circuit model using a simple lumped capacitor to model the probe. You can see the agreement is pretty good on the high side here, and we're predicting the low side, but the biggest disagreement is right in here. And it turns out that has to do with the capacitive probe. So we can fix that just by using a little bit more sophisticated probe model. Clearly our capacitor has 0 physical size, but our probe is actually fairly large in terms of wavelengths. It has significant length. So we wouldn't expect a simple lumped capacitor to do a good job of modeling that. But all we need is a few transmission line elements. That green is Teflon, so I've got my metal probe passing through a Teflon block. So this transmission line uses Teflon for the dielectric, and I compute what its impedance is. And then I've got the other 2 pieces of the probe hanging in air. So its dielectric constant is 1. And then we'll throw in some capacitance for the step discontinuity here. And most of this comes from just simple 2D cross-section simulations to basically find out what the impedances are in the 2 different spots. So if we put that probe subcircuit into our circuit theory model now and take a look at the comparison, now we're actually quite close. So I believe the circuit theory model. And in fact, practice tells us this over and over again. There's, the small discrepancy here is kind of an issue of tuning. I can actually tune the circuit model so that the zeros line up exactly, but then this peak will actually drop down. The peaks won't match the goal. So you can either make the peaks match the goal, or you can make the 0 frequencies line up exactly, but you can't get both. But this is 60 dB down anyway, so what about other types of circuits? What about planar circuits? Does all this still work? And the answer is yes, absolutely. Here's a Microstrip Combline circuit rather than the high Q circuit that we've been looking at. So we start with a Chebyshev Microstrip solution. Here's my ports out here on the ends where I'm going to do tuning with my circuit theory engine. And before I start trying to build the cross-coupling networks, I can hang lumped elements between these ports out here and again experiment with the cross-couplings and get a good idea whether what I want to do is achievable or not. And then I make a decision on how I'm going to realize those. And in this case, I'm realizing 2 triples, and I want a capacitive coupling. So I've got little interdigital capacitors here off the ends of the resonators that I'm growing in. So I start with 0 depth on those capacitors, and I just gradually move them in and re-optimize as I go, and that's it. And I never touch synthesis to do this. And the other beauty of port tuning is that it's very unambiguous. The capacitor hanging off this guy, if it's positive, it says the resonator wants to be longer. And if it's negative, it says the resonator wants to be shorter. And here's the tuning circuit. Again, here's the resonator guys, here's the coupling guys. The one thing I'll point out here is on these coupling capacitors where I'm modifying the coupling between resonators, if that's negative, it actually means you want more coupling. And if it's positive, it means you want less coupling. And that's because it's the wrong element. It should really be in an inductor. But a capacitor is easier for the optimizer to work on. Because as you get close to zero, the capacitor is either going to be a very small positive number or a very small negative number, and it passes through zero. If you use an inductor, it's either going to be a very high impedance positive or a very high impedance negative, and when it flips sign, it passes through infinity, and that tends to confuse the optimizer. So, and so here's the circuit response at this stage of the tuning. And this was the original spec here, and it looks like we're going to meet it. So zeros in distributed microstrip filters, zeros on the low side are hard to get. It's easier to get a zero on the high side, but this is a pretty flexible way to get some zeros on the low side of the response. So let's say a couple of words about 5G. The organizers asked me to say a few words. As far as handsets go and the filters in handsets, I think we'll continue to use the SAW and BAW and FBAR technologies. I don't think the handset frequencies are going to move up rapidly. They're going to have to stay where they're at right now, at least foreseeable future. There is something new, which is called single crystal BAW, that looks like it will allow that type of filter to go higher in frequency, maybe quite high, based on some of the work I've seen. So then the next level up is, how do you get more coverage? Well, small cells and micro cells. And there the issue is going to be the volume available in the package. The minute you reduce the volume, you're going to lose performance, and there's just no way around that. But of course, now you're talking about a much shorter distance too, so hopefully that'll be okay. Kind of the easiest thing to identify is the business of the millimeter wave backhaul. How do you connect all these guys back to the network efficiently? And clearly, the bandwidth is up in the millimeter wave region to do that. And the challenges are going to be cost and volume production. So here's, I looked around in the literature, and a lot of people are designing E-band radios. And so I took a quick look at an E-band diplexer. And so I designed a waveguide matched T-junction, and then had some prototype designs for the waveguide filters and hooked it all together in Microwave Wizard. And I've actually ported the optimizer to Wizard, and now it's talking to Wizard, and it's directly modifying the dimensions of the filter. It's putting the optimizer inside the optimization loop. This is something I swore for years would never ever happen, but we're getting there. Because these are mode matching models, they're very fast. When you start introducing some 2D or 3D FEM models in your project, then yes, it's going to slow down. But if you can keep most of this mode matching, this actually runs quite fast. And you can, again, get to a nearly perfect response then with the optimizer. And if you want to change the bandwidth or modify the center frequencies, that's quite easy to do. So again, on this E-band diplexer, I think the manufacturing issues are probably harder and more critical than the design issues. To eliminate most of the tuning, you need to fabricate that part to at least plus or minus 10 microns tolerances, and that's the combined machining and plating tolerances. Plus or minus 5 would be better, and I've talked to some people this week that are working towards plus or minus 2 or 3 microns. So you're either going to have to invest up front in precision manufacturing, or you're going to pay every day for tuning. So take your pick. You're going to pay one way or the other. And then, of course, there's some interesting packaging and interface challenges. You know, how do we get this mechanical, very high quality diplexer connected into our electronics? And there's some interesting work to be done there too. So what about new things? What breakthroughs could we hope for? Well, 3D printing, of course, is very interesting. There's been a lot of good papers this week about 3D processes. So materials and processes are going to continue to evolve, but you've got fundamental issues with surface roughness and, again, tolerances. Many of these processes, particularly the earliest ones, use some kind of resin or maybe even a ceramic-based process that's going to shrink as it cures. And so the most honest vendors will talk to you about near net shape versus near net size. Any process that has a lot of shrinkage, the vendor says, well, I can get close to the shape that you want, but the dimensions might not be exactly what you want. Versus what we really need, of course, is pretty precise dimensions to make all this work. What about LTCC? That's been around for a long time. Well, the new thing there is people are starting to etch circuits in LTCC. Normally, the conductors would be screen printed, and that's fairly low resolution. But I know of several people now that they somehow screen print or deposit the metallization and then etch it rather than trying to use a screen. And I've seen some pretty good results at KU band on an LTCC filter. You still, depending on exactly how they do this, you've still got some shrinkage issues with LTCC. Another thing you might want to go look at is there's this stuff called Apex Glass, and the company is called 3D Glass Solutions. They're in Albuquerque, New Mexico. And what this is, it's a composite glass ceramic hybrid material until you expose it to UV light, and the part that gets exposed turns into pure glass. So you've got pure glass supported by ceramic. And it has anisotropic features to it. So you can create some interesting 3D features with this. So I can imagine in my mind maybe SIW type structures at millimeter waves using this material. So that's maybe something that you want to look at. And in searching through the literature, I found this example. This is exactly the E-band diplexer that I just showed you. This was done 2 years ago. And if you look at the data in the paper, it's a diplexer, but the pass bands have shifted by about half of the bandwidth. And in one channel, the return loss is about 10 dB, and in the other channel, it was maybe only 5 dB. So it was a good early attempt. I think there's been some better results shown here this week. And of course, this is 2 years ago, and a lot of things happen in 2 years. Here's another very early result, again back in 2015. This was a group at Imperial College, and they tried to do a 100 gigahertz filter here at W band. And again, the tolerances and the plating shift. At 100 gigahertz, their passband was off by about 7 gigahertz. But again, this is 2 years ago, and things move along, and I think we can count on things getting better and more interesting. So, to wrap things up here, I think I've demonstrated that fast equal ripple optimization is a viable alternative to some of the traditional synthesis techniques. If it works well, I think it's a fast and intuitive alternative to design by synthesis. And it's actually a very key component in our port tuning of complex EM-based filter models. Again, if we're not coming back to the same solution every time, we're introducing error into the process. Our EM tools have become quite mature. They have a lot of capabilities. They're still adding capabilities. Every time I think they're done and there's no more to be had, they come up with some new idea. So that's still exciting. And because they're so mature, I think the accuracy of our simulations is really limited by our knowledge of the input parameters. You know, do we really know what our dielectric constant is? Do we really know what the metal thickness is that we just put down? You know, did we measure our dimensions of our fabricated part, you know, after it came out of fab? So that's really the limitation, I think. And we may see more and more EM simulation directly driven by the optimizer. We're not going to be able to do a lot of this yet, but again, I think this will evolve. And the port tuning is still, I think, probably the most efficient and the most effective method for optimizing a complex EM model. So thank you for your attention, and I think we've got time for some questions.